This is the SPC P chart example, the handout on Blackboard. You can see that I just put some of the samples and the number of defective bills. This is an attribute chart because we're not measuring anything on a continuous scale. And it's a P chart because we have a sample size, and the sample size is n equals 50. It's given in the problem. So that's a sample size, and then we're asked to use 3 sigma control limits, so z is equal to 3. And so P stands for the proportion defective. So how we calculate that is the number of defective bills divided by the sample size. So for the first sample, that will be 25 divided by 50, so that will be 0.5. For sample 2, it will be 22 defective bills divided by 50, that will be 0.44. And so on. 33 divided by 50 equal to 0.66. So you can do that for each sample and calculate the p-value for each sample, basically. Now when we come to calculate the CL, like we said before, can be calculated in this case as CL is equal to the average of the measure, which is P, so we can add all these P's and divide by their number, which is 16. So we can calculate it this way, so we can come and do 0.5 plus 0.44 plus 0.66 until we reach the end, 0.6 divided by 16. We can do it this way, but if all we care about is the CL value, we can do it in another way, which is the sum of the defects divided over all the samples divided by the number of the samples multiplied by the sample size n. So that will be easier to calculate if we can come and add how many defects there are. So we sum up the number of defects, if 25 plus 22 plus 33 all the way down. So we can write the beginning of it plus 22 plus 30. It's easier to add whole digits than to add decimals, and so divided by 16 multiplied by 50. Total defects is 513 divided by 16 multiplied by 50, and we're gonna find that it is 0.64. If you do it this long way, you're gonna find also that you're gonna get 0.64. Either way, you're gonna get 0.64. Looking at the formulas in the book, LCL is P average, which is the CL, minus 3 times the standard deviation, and this the standard deviation for this process, for this P chart, and the standard deviation in this case is P average times 1 minus P average divided by n, all of it under the square root. So this whole thing is the standard deviation. So we can calculate that by saying P average is 0.64 minus 3, and then under the square root calculate 0.64 times 1 minus 0.64, all of it divided by 50. So you would do 1 minus 0.64, multiply it by 0.64, divide it by 50, then take the square root of the whole thing. Multiply it by 3, put it in memory, and then subtract that total from 0.64. So you should get, if you do that, 0.44. So that's the LCL. Again, if the LCL is negative, you make it equal to 0. UCL is the same thing, P average, but now we put plus 3 multiplied by, again, the standard deviation. So we're taking CL like the average minus 3 standard deviation, the average plus 3 standard deviation. So if you do the plus, you should get 0.84. Is this process in control or not? We notice without graphing, if we were to graph, we would graph again, I don't want to graph, but the sample on the x-axis, we have 16 samples, so we will go from 1 through 16, and on the y-axis we have the P, so we will draw CL, LCL, UCL of the P chart, and we will make sure that all the P's, that would be all these values, will lie between LCL and UCL. That will be between 0.44 and 0.84. But given the criteria we're going to use in this class, we don't need to graph. All we have to do is come look at these numbers and ask ourselves, are all P values between LCL, which is equal to 0.44, and UCL, which is equal to 0.84, question mark, and we can immediately detect that this one, the whole sample, was defective. So the answer is no. Sample 12, at least even if you find one sample that is out of control, that means out of control, that means so the process is out of control. Again, we're not going to do anything after that. In the real world, you would stop the process, and you will investigate why that sample was out of control. You would remove the causes behind what made it out of control. You remove other samples, the causes behind other samples that were out of control, and you will fix the problems, and you will continue to monitor the process. Recalculate the LCL, CL, and UCL, and continue to monitor the process. That's it.